All right, I think I got it. So today we're going to talk about torque. Torque is related to uh, it's related to that's funny. Um, Rotational force and hold on, I'm kind of having an issue here. Erase all the slide. All right, so now I think I got it. So this is the Greek letter for tau. Um, it's pronounced tau. So we use that for torque in physics. And then R is for the radius of the circular path. And F, of course, is the force applied. And so torque is equal to the force multiplied by the radius of the circle. So if you want to think of this as a circle, the distance from here to here is the radius, right? Because I'm going to sweep around this way. And then how much I push with my hand, that's the force. And so if I were to measure the torque that goes right here, and the torque is like a circular or rotational force, the torque would be equal to whatever the radius is in meters times the force in newtons, right? So it would be Newton meters, okay? Whew, that's a lot of work. All right, let's keep going. So, a couple things here. This box is initially at rest, and there are two forces acting on the box. There's at the bottom of the box, this is pushing in, and at the top of the box, it's pushing this way. So this is pushing this way, this is pushing this way. What do you think will happen to the box? Well, the box should rotate, right? Now, the net force of the box is 0 currently because the box isn't moving. But will the box move? Well, if there's enough force, it will rotate, okay? So because the force isn't exactly in the same location, I'm going to have some torque. So the center of the rotation would be like the center of the mass, right? And since the box is a perfect square, and then the line of action is, we'll talk a little bit more about it, but the short answer is yes, the box will rotate. It will rotate in this direction here. It'll go that way, okay? So while these two forces add up to produce a 0 net force with regards to translation, translation is just the box moving left to right, it will create a torque which will cause the box to rotate. And that's going to be important for our roller coaster project. We need to understand that things that rotate have torque, which is a different type of force. So then torque is a rotational analog of force, okay? If push or pull describes a force, then twist describes a torque. So the same force can produce different torques depending on where it's applied because it's a product of the radius. So the further away this force is from the center of mass, the impact it has on the torque. So let's think of a door that opens. So a 50 Newton force is applied to the door at 3 different locations. If the force is applied here, I have a greater radius. So if I have a greater radius, I'm going to see some wonky stuff happening. What does that mean? Well, the force can be the same, right? So I can have the same force, but the radius is different. So think of this as like the center of the circle. Think of this as the center of the circle, and the radius is all the way here. So that's a bigger radius, although I still have the same amount of force. But you have to remember that the torque is equal to the radius times the force. So out of all of these, A is going to have the greatest force. B, the radius is much shorter. Even though the door swings way over here where I apply the the torque would be less. So right now, A is the greatest force. The force of A is greater than B. And then over here, I have an even smaller radius. So the force of A is greater than B, and the force of C is less than B. So if they're all being a 50 Newton force, because the radius is smaller, I'm going to have a different type of thing. So which one is more effective in opening the door? Well, A. So when you go to open a door, and just watch the next time you open the door, notice that all the door handles are far away from the hinge. They're all the way over here. Some doors have a handle right here for decorative purposes, but it's always easier to open the door way over here than here. Okay? So A would be the most effective because the distance is greater. And so here's another example of this. The line of action is the imaginary line in the direction that the force passes through the point of the application. So that's the line of action. The next thing is, torque is created by the force depends on the perpendicular distance between the center of the rotation, in this case the hinge, and the force's line of action. So the line of action is the straight path that the force is applied, and then the perpendicular distance is the radius of the circle, right? So can you imagine this is a great big circle, and the radius of the circle is the perpendicular distance. So then torque, T, or tau, is the force applied by the perpendicular distance r. The perpendicular distance r is called the lever arm. Torque is a maximum when r is the greatest. So if this is 50 meters and I want to find the torque, or 0.5 meters, a half a meter, I simply plug that in and I get that 0.5 meters times 50 newtons is 25 newton meters. So that's the torque of A. Now, if I were to do that with B, it would be smaller. If I were to do that with C, it would be even smaller. I kind of skipped over the slide because I accidentally hit the button twice. So in SI, in our physics class, we always want newton meters for torque. There is a foot-pound thing that goes on, but that's a different thing. So I'm going to skip past all of this stuff, but basically you can enter in numbers. So for example, if I apply a force of 60 newtons and the distance and the torque is 480, how do I find the distance? Well, remember that torque is equal to the radius times the force. Well, they gave us a force and the torque. And I said that backwards, but 480 newton meters is equal to the radius times 480, not 480, times 60. So then I just divide by 60 on both sides. And so 480 divided by 60 is just 8. And so that would be 8 meters, because the newtons would cancel, right? This is newtons, this is newtons, this is newtons. So the newtons will cancel with the newtons. I get 8 meters is my radius. And so basically they're saying there's an interactive that would calculate that. So you can find these torque calculators on the internet, but you don't need it. Just plug it into the formula, okay? And then if you were given a distance of 0, what's the torque? Well, if I apply a force of 50 newtons right here, the distance is 0, it's still the same, right? The torque would be 0 because I have R times the force, which is equal to 0 times 50, which is just 0 newton meters. Okay? And so I'm not going to go through all these examples. Torque can be positive or negative. And so positive is going to be counterclockwise, and negative would be clockwise. And it's just the way we have it set up. That's the common convention. So if you're, and I mean, that's it. I don't want to explain it anymore. That's pretty simple. Okay. So now look at this. This is a circle. So the radius here is equal to the radius here. And it says, what is the sign of the force? Well, the sign of the torque. So because this force is going in this direction, then it's going to cause it to rotate this way. And because there's a force going in this direction, it's going to cause it to rotate this way. That's clockwise. So that would be negative, right? Okay. And then it says, well, it breaks it down into two of these, right? So it says, what is it if based on F, and then what is it based on 2F? Well, this force will force it this way, which is clockwise. This one will force it this way, which is clockwise. So it's clockwise for both of them. The next thing is the center of rotation. The same force can create a very different torque depending on where you place the center of rotation. So this is an interesting thing. If this is in the center, this has a little bit to do with center of mass, but if I applied 10 newtons here, remember that the torque applied is equal to, this is supposed to be an equal sign, the radius times the force. Okay? So then this would be 2 meters times 10 newtons. So the torque here is 20 Newton meters. This is 1 times 10, so this will be 10 Newton meters. This one, oh wait, we got to be careful. This is positive 20. What's this one? Well, remember that it's rotating this in the negative direction, so then that one would be negative 20 Newton meters. Okay, does that make sense? And that's where that comes from. So just like before, remember that counterclockwise is positive and clockwise is negative. Now, net torque is the sum of the torques. So we have to calculate the torque going this way. That has a value. And we have to calculate the torque going this way. And it's the sum of the torques. Okay? So let's do this side over here. So this one, I've got 1 times 10. That's a negative 10 Newton meters. That's counting 1 times 10. Then if I do, this looks like it's 1/2 times 10. So that's a negative half of 10 is 5 Newton meters. Then over here, because it's rotating counterclockwise, it's positive, and it's 1 times 15, which is 15 Newton meters. So when you add them up, this is negative 15 Newton meters. So you have 15 minus 15 Newton meters, or 0 Newton meters. So there's 0 torque on that. Does that make sense? So the beam will just stay still. The total net is 0. Okay. That's it. Okay. That's it. That's all I got.